Welcome to Numerical Ship and Offshore Hydrodynamics. Today we are going to discuss about the Froude scaling, okay, and these are the keywords that we are going to use to get this lecture. So, let us come back to our topic, which is the Froude scaling. Now, when you do the experiment, normally you are doing in the model scale. A ship, normally conventional ship, the length would be the scale of 150 to 200 meter long, right. So, therefore, going a full scale experiment is really tough. So, then what we do in lab, we do the experiment in the model scale and then we try to find out what would be the forces or the parameter that we measure in experimental in model scale, what would be that in the full scale, and therefore, we have to do some scaling factor. So, we do here the Froude scaling. Now, if you look at here that we are using that, let us say LS, BS, TS be the length, breadth and the draft of the original vessel, or you can call it a prototype, and then we have LM, BM, TM would be the length, breadth and draft of the model scale vessel, and we maintain that length of the full scale vessel by length of the model scale vessel is equal to length of breadth of the full scale vessel by beam of the model scale, and also the draft also, the ratio also is similar and equal to lambda. Having said this, let us try to find out how we can scale up certain parameters. So, let us start with how we can scale the volume. Now, you can see that volume is nothing but of course, you are doing the dimension analysis, the length cube. Now, you can see that length is modeled by lambda. So, definitely the volume should be scaled by lambda cube, right. When you understand that volume is scaled by lambda cube, then we can do many parameters also we can scale. Let us see that how we can scale the time periods. Now, you see here I am using the formula for time period, which is mass divided by the spring constant. Now, here just for sake of clarity, we are using for the heave modes. Now, in heave modes, this nothing but the mass divided by the restoring force, which is rho g into AWP. Now, here you can see that I did not write the AWP because most of the time that water plane area is not available. However, which is available to you is the water plane area coefficient. Now, when you design a vessel that is already maybe taught in the hydrostatic courses, basic hydrostatic courses, we are going to define so many design parameter. One is called the block coefficient that we discussed before. We did not discuss the water plane area coefficient or midship area coefficients. This basically when you do the design, then a designer can assume that okay, that would be my the water plane area coefficient, and with the help of that we can get the area using this formula, that rho g CWP equal to LM, I mean it is CW multiplied by the length into breadth, right. So, from here you can see that very quickly we can get the water plane area if you know the coefficient of the water plane area. Similar to the volume, if we know the block coefficient, then multiply the block coefficient by L into B into T, we will get the volume. Similarly, if we know the water plane area coefficient, then we can multiply with the length and beam, we can get the water plane. Anyways, now this is how we can get this the water plane, and then we can just cancel out the similar terms. So, that we cancel out the rho, right, we cancel out the coefficient, because this coefficient should be same whether it is a model ship or is a actual ship. So, therefore, we have this expression T s equal to delta s by delta m, that means displacement ratio, as well as the length into breadth by full scale divided by length into breadth for the model scale. Now, you know that this displacement is lambda cube, as we mentioned over here, you can see here, and also you can see the other parameter is lambda square. So, it is lambda cube by lambda square. So, therefore, the scaling of time period is root lambda. Okay, fine. So, now let us see what the other parameter that we can scale. Now, we are doing the velocity. Now, velocity is the L by T, right. Now, I just rearrange it, L by T equal to Ls by Lm, that means the ratio between the actual ship by model ship length divided by the time period of the actual ship by model ship. So, I know that this lambda s by lambda m equal to lambda, sorry, Ls by Lm equal to lambda, and Ts by Tm is equal to root lambda. So, I understand that velocity can be scaled by root lambda. Now, let us see the acceleration. Then formula for acceleration is L by T square, I mean that is the dimension analysis we do is L by T square. So, again that I can arrange the similar way, which is Ls by Lm by Ts square by Tm square, and then we can see that it is L lambda divided by root lambda square, which is lambda. So, acceleration is order of 1. Now, once you understand that acceleration it is scaled, you cannot, it is similar for model or for the ship, it is order of 1, then we can really scale the force. So, how we can scale the force? It is mass time, acceleration. So, I just here mentioned that Vs is nothing but the volume. So, volume of the ship, we can call displacement, I mean delta also, here I am using the V. So, so mass and then rho will cancelled out. So, therefore, essentially the ratio of the volume and then multiplied by the ratio of the acceleration. So, from my previous slide I know that ratio of the volume is nothing but lambda cube, and then acceleration is order of 1. So, therefore, that I know that my force is the order of lambda cube, right. Now, once I know the force is also lambda cube, so let us try to find out how we can scale the damping and the added mass, right. Now, you see the added mass also a force and damping also a force. So, definitely my right hand side should be lambda cube, right. So, let us see that what is there in the left hand side. Now, I know that right hand side is of course lambda cube, and left hand side also added mass, also the added mass force is added mass multiplied by the acceleration. So, therefore, it is the ratio between the added mass of the prototype divided and model multiplied by the ratio of the acceleration equal to lambda cube. Now, as you know that Vs dot by Vm dot, that ratio is equal to 1. So, therefore, I understand that added mass also can be scaled by lambda cube. Now, let us see how we can scale the damping. Okay. Now, in damping, in the right hand side of course, it is lambda cube because it is force, and in the left hand side it is damping coefficient multiplied by the velocity that represent a force. So, now if you do the again the scaled analysis, this Vs by Vm is definitely is root lambda, that we have found out, right, that velocity, the ratio of velocity just we found out is a root lambda. So, therefore, that Bs by Bm multiplied by root lambda definitely equal to the lambda cube, which is the dimension of the force. And from here I understand that damping actually we can scaled by 2.5, lambda to the power 2.5. Now, this is how we can do the scaling for the different parameters that actually we can measure through our through experiment in lab. Okay. So, how we can conduct the experiment to get the damping and added mass, we have already discussed it before. So, in connection to that, once we have the damping coefficient in scaled model or the added mass in the scaled model, and sometimes the natural frequency also you can get through the scaled model, and then we can use this scaling factor and we can guess that what would be the added mass in the real ship, what would be the damping coefficient for the real ship, and what would be the natural time period for the real ship. Okay. So, now let us see one let's solve one problem. Now, it is written that a model ship is excited at 1.5 second wave. Now, if you maintain the Froude scaling 1:36, so that means that lambda scaling of lambda is 1:36. Okay. So, then if it is used, that means that length of the ship by length of the model equal to 36, right. That is what the meaning of 1:36 scaling. So, the question is asked that what the time period of the incident wave at which the full scale ship may be experience high response. Now, we discuss in seakeeping that in the natural time period, only in natural time period, that ship tend to experience the high response, right. So, therefore, here it is given that that natural time period we can guess, because it is not explicitly mentioned here, that model ship is excited at 1.5 second wave. It means that natural time period is 1.5 second, right. So, if it is so, then we try to find out what is the natural time period for the real ship, and scaling also is given 1.36 second. So, the model scale the time period is 1.5 seconds. So, we are using the Froude scaling. So, Ts by Tm equal to root lambda. So, here the lambda is 36. So, therefore, that root lambda should be equal to 6, right. And then we understand that T, I mean the time period of the real ship divided by 1.5 is the time period for the model scale, it should be equal to 6. And therefore, we can find out that our in real ship a 9 second wave can cause a huge damage. I mean, I do not say, I mean, it is a high response. So, I can't say whether it is a damage or not at that particular, anyways. So, this is how actually we can solve some problem using the Froude scaling. Sometimes, in fact, it is possible to share the both of the data, like we can say that what is the natural time period for the model scale, right, and also we can say the scaling factor, and also we can say that what is the let us say CWP coefficient, and one can ask that what would be the added mass also. So, let us see, let us go back and just see that what I said just here. So, here here you can see that sometimes might be given that that what is the model scale, the scaling factor is given to you, and also it is given to you is what is the value for the model time period, this also given to you, and also the CWP will be given to you. So, if the all the data is given to you, some even one can ask what would be the natural time period for the what is the added mass for the ship. So, in that case you have to use this standard formula and use the Froude scaling, and you can solve the problem. Okay. Anyway, so let us move on. Today we are also going to discuss some more problem. So, let us take the next one, this. Okay. So, it says that consider a 150 meter long barge, I mean uniform rectangular cross section. So, that means that each cross section it is uniform, and it is 25 meter, and then the draft is 10 meter, and assume that we have a 90% of the mass can be considered as a added mass, right. So, it says that at 0 speed what the at what frequency of C waves will produce the largest heave and roll motion. And also it is given that we there is no damping, right, and then that the rigid body roll radius of gyration is equals to the half the breadth. So, it is half of 25, which is 12.5, and also kg is given. Okay. So, now how do I solve this problem? So, let us first write that what is the formula. Let us solve the first problem and try to figure out what is the formula for the natural time period for or frequency for heave mode. Now, this data are given to you. So, L equal to 150 meter, B equal to 25 and T equal to 10 meter, and also that it is given that it is 90% of the mass should be your heave added mass. So, it is A33 is 0.9 into m, right. Okay. And now, this is the formula for your frequency. It is rho g AWP divided by m plus 0.9 m. So, I replace everything m I can replace rho into L into B into T, right, and also you can replace that water plane area nothing but L into B. So, if we do that, so I can I know that this expression will come, right. So, AWP I replace by L into B here, and also that mass actually I use this rho into L into B into T. And now, I can cancel the similar terms. So, rho is cancelled out, L is cancelled out, B is cancelled out. So, finally, I got that it is G divided by 1.9 into T. So, just I am taking approximately G is equal to 10 meter per second square and T also 10. So, then I can get omega 3 equal to 1 squared up 10 by 19, and I got the value is 0.725. Frankly speaking, we really do not understand much. We cannot visualize the frequency. It is much more clearer to me, at least for me, to know that what is the time period. Now, if I just time period, if you use the formula, it is 2 pi by omega, and then we can find out that natural time period is almost 9 seconds. So, what is meaning? It means that a 9-second waves if hit that shape, then it can have the high oscillation in heave mode. Okay. Now, so actually this problem gives some nice practical feeling that I am going to discuss after this the problem. Now, let us solve the next problem, which is here you can see that added moment of inertia for roll is ignored, okay, and radius of gyration is given. So, so this is the basic parameters, and this is the formula for the natural frequency in the roll. So, rho g delta into GMT and m into kx square. So, again I substitute m by the rho into V, that means the volume, or rho into delta, and then if I cancel the similar terms here also, the rho and delta will cancelled out. So, finally, so I have this omega into G into GMT by kx square. Now, this the radius of gyration is given there, it is half of the breadth. So, it is 12.5. However, I have to calculate what is the value of GMT, right. Okay. Yes. Okay. So, let us see. Now, here we are going to use this formula to finding out the GMT. Now, we know that the Kb plus Bm equal to Kg plus Gm, right. Now, this is already discussed in our initial days lecture, right, and I think you all know this the formula very well. So, I just physically I can demonstrate here. So, this is the pen here. So, this is the last point we call the kill, right, and then you can take then G sum over here, and B may be sum over here, and M may be this. So, I just say this Kg plus Gm should be equal to B is sum over here. So, Kb plus Bm, right, and then from there I can get Gm equal to Kb plus Bm minus Kg. Now, here I will tell you that since it is applicable in case of a roll or in case of a pitch also, I did not mention explicitly this GMT or GML. In both the cases, Gm equal to Kb plus Bm minus Kg. Now, in case of a roll, that BMT is I axis by delta. Okay. So, here it is written. So, it is I axis by delta, and then it is I axis is nothing but L B cube by 12, okay, and volume is L into B into T. So, this is very well known, right. It is L B cube by 12. It is this is the for a rectangle. This is the second moment of area. Everybody know that. So, nothing new over here. So, I can get it this equal to B square by 12T, because if you cancel out the similar term, it will become this B square by 12T, and then value is 5.20. So, in case of a GMT, I am using that BMT, I use 5.20, and now since the draft is 10. So, since the draft is 10, so therefore, that buoyancy should be the middle point. So, I can take this as 5, and Kg is given is 7.5. So, therefore, I can get the value GMT equal to Kb is 5, Bm is 5.20, and Kg is 7.5. So, the value is 2.5, right. And then we have that omega 4 equal to, just use this formula, I can take G is 10 meter per second square multiplied by 2.7 by 12.5 square, and this comes out to be 0.415 radian per second. So, here I get that value is 0.415 radian per second, and let us take that what is the value here, the time period, because it is, you are much more comfortable with this time period. Now, you can see here it excites at 15 point, almost 15.5 second, which is very normal in ocean going vessel. That is what we discussed during our lectures about the natural time period of heave mode, roll mode and pitch mode. I discussed that in case of a roll, it is much bigger compared to the, not, it 5 seconds is huge actually, I will tell you. Normal in ocean normal, it is mostly it is 10 to 20 second waves that is actually operating the sea. So, therefore, this roll is very much into that domain. However, heave is 10, so still it is better. Now, here let us try to, this is not there in this problem, let us try to find out the pitch natural frequency. Okay. Now, no data is given to you for pitch, but still we can approximate. So, that is how I say that it is always, of course, we are going to do everything numerically, we do from the first principle, and we solve this problem from the first principle, I accept, but however, it is always very important to get some engineering idea about the thing, so that at least you can do some very quick estimation and you can find out what is the natural frequency, or such some basic things like this. Let us see, here we do not compute anything, we are just using some kind of approximation. So, this is the given to you. Now, what I approximate first, that and pitch added moment of inertia may be the 50% of the that moment of inertia, pitch moment of inertia. So, added moment of inertia I take is a 50% of this. So, therefore, in the denominator I am taking 1.5 m into kyy square. Okay. Now, we need to approximate so many things over here, right, because again that volume will cancelled out, and then we have the G into GML divided by 1.5 into kyy square. Now, nothing is known to me, right, GML I do not know, kyy I do not know, right. Then how do I understand that what would be the possible natural frequency for this particular vessel? Now, here comes the idea of the approximation. So, I just approximate my GML equal to BML. Now, simply you can take here that instead of L B cube by 12, it should be L cube B by 12. So, you leave with earlier it is B square by 12 t, now you have L square by 12 t, that you can do, no problem. Otherwise, what in fact I did not do that also. What I did is basically I am taking simply BML is the order of length, so 150. See here the whole point is to approximate, we are not computing anything. Similarly, I am doing with the KYY which is 0.3 into L. So, I just take the 1/3 of the length. Now, with this approximation, if I try to calculate the natural frequency, it comes out 0.60. Now, if you just do that, it comes out 10 seconds. Now, you see like it is very much in practical, in realistic answer I get that normally that heave and pitch time period are very close by. So, it is also comes out 10 second and then heave comes out in the 9 seconds. So, you can do the same conventional process that I did for the roll, because kg is given to you, you can simply find out what is your GML directly, right. And also you can take that ky is 1/3 of L, that also you can take and you do the analysis and you can find out that what would be the it is T4 is given, it should be T5. Okay. Anyways, so what is the natural now here what the interesting observation I want to make as follows. Here it is 10 second for pitch, it is almost 10 second for heave. Now, you see suppose a 10 second wave is hitting the ship. Now, then the ship will excite both in heave and pitch mode. And why? That is what I said, it is very important to know the information about the phase. Now, you see in both situation heave and pitch excited by a same wave, and then both tend to get to the maximum amplitude. Now, if both coming at the same time, it means that it is heaving maximum, at that time pitching also maximum. Now, you can see that how much of bending moment will come in this particular case. So, that is why this phase is also very important. Now, if I see that both are not in a 10 second wave, but both have a phase, like let us say it has a let us say some 10 second or sorry 0.1 second phase lag. So, therefore, when he got maximum, pitch may not be get maximum at the time, maybe pitch may be the minimum at that particular time, right. So, that is why this problem gives a very nice idea about when that is why this coupled equation motion analysis is also very important for us, right. Okay. So, with this I have one more problem. So, let us very quickly see this problem and I will I leave that most to you to do this in home. Okay. So, this is the problem, we have the rectangular again we have a rectangular barge with the length is L, B and T, and it is given that the sectional added mass is given to you, which is the area of the semicircle whose diameter is equals to the beam, right. So, now then you have to find out the added mass coefficient with respect to B by T ratio. So, this is the problem. Now, how to do that? Now, here is given the sectional added mass is nothing but that area of a semicircle whose beam is equals to the whose radius diameter is equals to the beam. So, therefore, the area is nothing but pi b by 2 square for the circle, and then if you multiply by another half, then it is the area for the semicircle. Now, if you multiply by the rho, so it is a mass, and then if you multiply by the length L, then it becomes a the volume. So, it is that dimension equal to the dimension of the mass. So, I understand H is equal to pi rho b square L by 8. Now, what is the dimensionless quantity? So, I just divided the added mass by mass. So, mass term is LBT and this is the added mass I just compute here, and if you cancel out the similar term, it becomes pi by 8 by b by t. So, this is the first part of the question. Now, if you replace by b by t by 2, 3, 4, then you can find out what is the ratio. Next question is what is the natural time period for the undamped system. And now, this is the formula for the undamped system, right. So, now what you can do over here, I know the ratio A33 by m. So, I can divide the whole thing by mass and I replace the mass by rho into length into breadth into t, and then added mass by and then sorry AWP is L into B, and again you can cancel out the similar term, and finally you have this term T3 equal to 2 pi T into 1 plus pi by a into B by T. Now, you can put B by T ratio 2, 3, 4, and you can take that the T equal to 4, and then you can find out what is the natural frequency for this particular vessel with different B by T ratio. Okay? Fine. So, just work out this and find out there's numerical values. Okay. So, with this let us stop today. Thank you.